Today I'm going to share my recent research on robust and certifiable state estimation from EKF, FGO to SDP, and their application to GNSS-based localization. Wow, such a long title, isn't it? So I will try to make this fun and interactive. Please feel free to interrupt me anytime you have any questions. Okay. It's coffee time now, and I guess most of you are getting a bit hungry and a bit sleepy. What about we order some coffee together? Yeah, here's the drawing carrying delivery boxes. And I have used the autonomous robots to order a coffee before. And this is one of our past projects using the GNSS localization for the autonomous delivery. Let's watch this video together. So our coffee is made from a cafe several miles away, and it will be first carried by a drone. But don't worry, there's no drone crash today. And then the drone will match our ground vehicle at an open sky environment in our campus. Then they have to interact with each other using the GNSS localization. Let's wait. Yeah, we did it. Then based on the GNSS positioning up to centimeter level, we can get the coffee in time. Now let's order our own coffee now. This time, the robot meeting spot is near a tall building. Let's see what will happen. Oops, looks like Murphy's Law strike again. Anything that can go wrong will go wrong. It says that, but what's the cause for this failure? Can anyone tell me? I have mentioned the hint before just now. Yeah, please.
I'm assuming if it's GNSS-based, you'll have error within 2 or so meters. So
yeah,
localization points are jittery.
Yeah, that's right. Yeah, very good answer. In this second try, actually, in the second try, we have the tall buildings near us. So it blocks the GNSS signal and it leads to a wrong positioning result. So finally leading to the failure. And don't worry, if you want coffee next time, you can call me and we can have another try together. Yeah. So this example just tells us 2 needs for the state estimation. First, the state estimation should be resilient against disturbances from the environment. For example, in this example, the disturbance is from the tall buildings, and we call this robust. And the second need for it is that it should provide states with correctness guarantees. For example, in this example, the interaction is successful or fail, and the robot should just tell us whether it is successful or failed, and ask for help from the people if it failed, and we call it certifiable. So in the following, we will follow these 2 rules and try to do some research to achieve them. Actually, the delivery robot is not a new thing in Canada or even Ontario. In Ontario, the delivery robots are operating on the roads every day now. And to protect the safety of the citizens, the government and related organizations have announced more and more regulations and also updated them year by year, including the cargo transportation, the artificial intelligence, and the robots and cobots, also the connected autonomous vehicles. It seems that both the robots and the regulations are ready in Canada, but how about the safety of them? Let's look at the safety under supervision by 2 viewpoints. The first viewpoint is from the consumers. In this year, a recent survey found that 46% of the Canadian consumers still do not trust the autonomous driving vehicles. For example, this picture shows that a self-driving car crashes into a delivery robot on LA Street. A little robot can cause a huge damage. Wow, what's that? And from the second viewpoint is from the companies. The companies is also trapped in a dilemma. Should they totally believe they are robots or not? And their current answer is the second. Due to the immature technique, the self-driving car companies still employ drivers or safety monitors behind the screen to control the robots. And there's a joke that the self-driving car still have drivers behind. As a researcher, I also face this question. And our objective is to solve the scientific challenge behind it instead of just providing an engineering solution. So the question is that, what are the scientific challenges here? To answer this question, we have to provide the outline of the state estimation here in 3 steps. First, the robots are equipped with sensors like the GNSS sensors, the inertial sensors, cameras, and lidars. And this sensor could provide raw data. And then the raw data will be pre-processed in the module and the front end. Then the front end will convert the raw data into abstract equation in math. And finally, the state estimation, also named backend, will process abstract equation and output the state, including the position, velocity, and attitude. In this talk, we will focus on the estimation, the backend, and assume that the 2 modules before it are immutable. We provide 4 types of mainstream estimator here, from the most classical one to the most advanced one, including the least square LS, the extended Kalman Filter EKF, the factor graph optimization FGO, and the Semidefinite Programming SDP. Their position is decided by their ability to cope with these 2 challenges from both the non-Gaussian noises and the nonlinearity model. Now, it's time to tackle these 2 challenges and describe their details now. So let's again assume that there's a UAV and a UGV working in the urban areas using the GNSS localization system, which is also a range-based system. First, we focus on the non-Gaussian noises. The GNSS is designed as a range-based localization system, and the receiver here, the black one, should receive the signal along the line of sight direction from the satellite. And it is designed with a Gaussian noise, which is denoted by the black curve. However, there could be some obstacle here, or the shelters. They could cause the multipath effect and result in the red one here, denoted in the non-Gaussian noises. We will talk about the effects of the non-Gaussian noises later. Now we will turn to the nonlinearity. I will give you a simple example here in 2D case. The red dot here denotes the local optima, and the green dot denotes the global one. This seems like a really simple one. We can solve the global optimum in polynomial times. However, when the dimension of the problems increase, it could be more difficult, and it could cause lots of time to search it. So I believe that these 2 challenges appear among almost all the state estimation problems and all the robotic systems. The question is how to deal with these 2 problems or 2 challenges. Now I will introduce the first part of our talk, the EKF and the FGO. Why do I don't mention the least square here? This is because the least square only deal with the problem using linear model with Gaussian noise. And now, before diving into the EKF and FGO, I will first introduce the foundation of them, the maximum posterior estimation, MAP. The MAP cost function aims to maximize the posterior probability of the X. Here, the X denotes the set of the state, and Z here denotes the set of the measurement. Finally, the U denotes the system input. Following the Bayes theorem, we can divide the posterior probability into 3 groups, from the prior to likelihood and also the propagation. We denote them in the right figure also. First, we got the prior, which represents what we already believe. And the likelihood denotes that how the measurement could support or contradict our belief. And the propagation describes that how the system input can be used to update our belief. Finally, using all the information above, we can get the best estimate from all this information. So we have known what the MAP works for. Now we will turn to the non-Gaussian challenge in EKF or KF, the Kalman filter. The Kalman filter here, I have to say that it simplifies the MAP based on two assumptions. The first assumption is the first order Markov chain, and the second is independent Gaussian noise. And we describe these two assumptions into this right figure. These two assumptions allows that the KF to work in a recursive way. First, we get a prior probability at the epoch k-1, and then we can update it and we can predict the propagated probability at the epoch k. Then also with the measurement at epoch k, the zk, we can estimate the best estimation, the posterior probability from it. However, if there's non-Gaussian noises here, the noises can be also accumulated along this chain. So how does it happen? Let me rewrite the propagation and update formula of the KF here again. Here we use the same color of the formulas as the same as the right figure, and provided that we have the prior probability at k-1, which is the blue one. We assume that it is Gaussian, it is in Gaussian noise, and it is not polluted. However, the propagated probability can be non-Gaussian, then it can be accumulated along this chain. After that, in the update stage, there is also other non-Gaussian, for example, from our multipath, from the multipath effect from the building, then it could be absorbed along this chain. If we updated them time by times, the color could be darker and darker. It means that our filter believes our state is there, is true. However, it is really far from the ground truth. For example, there's a car here. The filter could believe that this car is on the road. However, this is a biased state. The actual state is maybe of the road near some obstacles, which could lead to serious accidents. So how to solve this challenge? We'll introduce the FGO here. The FGO and the EKF share the similar structure. First, the EKF structure can be represented as this recursive chain, a directed recursive chain. And the FGO here is also the undirected bipartite graph, including the state nodes and the vector nodes. They share the similar structure, right? However, in more application, the vector graph can explore more connections between the multiple states and multiple vectors. For example, this GNSS in localization systems, the batch FGO in this blue line could eliminate the non-Gaussian noises before and increase the accuracy greatly. This is because the FGO breaks the assumption in first order Markov chain, and it can be also solved by iterative nonlinear optimization. However, we still have a question here. So these two estimators share the similar structure, and they are both derived from the MAP. So what's their relationship in theory? Current research in the navigation community only compare them in theoretical way, but not in heuristic way, but not theoretical. And second, the setting in this figure, the blue line and the red line, could be unfair enough. So this is the research gaps here. To answer these questions, we have proposed and released an open source toolbox to comparing the EKF and FGO this year. They are in this green table. Compared to the existing works in this blue table, there are two main differences here. First, we compare more Kalman filter variants, the KFV in the green table, more than the EKF only. For the KFV, it also supports multiple linearization and also the robust kernel more than the EKF. And second, the second difference is that we focus on the sliding window FGO, the SW FGO here, more than the batch processing mode. This is because the filter only uses the data up to date, but not all the data from the past or the future. Therefore, we aim to compare it in fairly way. So the existing research has tried to compare the EKF and sliding window together and leading to a common myth. Is sliding window FGO better than or robust than EKF? We try to answer this question by expanding the EKF to a KF family, including the original Kalman filter, the interactive EKF, the robust EKF, and the combination of them, the robust and iterative EKF. However, there's still a gap between the RIEKF and the sliding window FGO. This is caused by the Markov chain we have mentioned before. So we propose a recursive FGO algorithm here to bridge this gap. So far, I have mentioned a complete chain from the EKF to the sliding window FGO. It seems that it's so smooth, and the relationship between the EKF and other Kalman filter variants are already well studied. So the only problem here is how to implement our new recursive FGO to imitate the Kalman filter variant using a vector graph optimization way. Here, we will describe our new findings. First is the structure of the Kalman filter variants. All of them adapt the same process, including a predict and an update step. Now we will try to simulate it using the vector graph way. First, we add the new state prior constraint and the propagation factor, finally the marginalization process to imitate the predict stage, and then also the measuring factor and Gauss-Newton estimation to imitate the update stage. And our key finding here is that to follow the Markov chain, we have to replace all the factors with only one prior factor. Finally, we also provide the sliding window FGO pipeline here. The sliding window FGO only adapts one estimation stage, and it maintains all the factors and all the states together in one graph. So let's look at the results, how they perform. Here, the FGKFV denotes that the recursive FGO algorithm that we propose using the same configuration as the KFV. And we use 4 configurations here from the EKF, IEKF, REKF to RIEKF. There's at least 2 new findings here. First, the KFV and the recursive FGO, which are denoted by the gray circle and a gray cross, they coincide together in all 4 figures. It means that we have successfully imitated the KFV using the vector graph way in both theoretical and numerical way. Second, our second finding is that the interactive linearization and the robust kernel could be useful in some specific configuration. For example, we have an initial point here, which is far from the ground truth, and making this model highly nonlinear. And the interactive linearization have limited compared to this figure. You can see the trajectory is more smooth. And also, the robust kernel can eliminate the non-Gaussian noises and become more smooth too. And finally, after combining the multiple linearization and the robust kernel, our final RIEKF achieved the most smooth and accurate trajectory. Then we also compare our recursive FGO using the EKF configuration with the sliding window FGO. It finds that if the window size is 1, then the error could be larger. Why? This is because they adopt the same smoothing propagation factor, but overweighting it, which leads to a smooth but inaccurate trajectory. However, if the sliding window size is larger, then the error could be decreasing, which means the potential of a larger sliding window. So it is heuristic. And here we list our two conclusions here. First, the KFV and our recursive FGO can be equivalent with spare settings and spare settings. And the second, these options like the iterative linearization, the robust kernel, and sliding window are all heuristic, and they should be used in suitable problems. Okay, we have completed the comparison between the EKF and FGO. You can see there's a question leading by the last page, meaning the small sliding window and large sliding window. We know that the larger sliding window can have potential to eliminate the error of our positioning. However, it could also increase the dimension and the complexity of the feasible region. As you can see in this figure, in a larger sliding window case, the searching for the global optimum would be difficult. And to solve this problem, many people employ the local searching methods. However, they can only provide local optimum, and they could fail without notice. This is one of the cases adapted from the existing work of David Rosen. It described a post-graph optimization problem, and it failed without notice. So how to deal with this challenge in nonlinearity? I will try to introduce a new notion here named the non-convexity. So according to convex analysis from Rockefeller, when is an optimization problem hard to solve? Here he said that the key distinction is not linear or nonlinear, but convex or non-convex. Now I will give you a simple example to explain this. We again use the green dots to denote the global optimum, and the red dot denotes the local optimum. First, in the left figure, there is the linear and convex model, and there is only one global optimum here, since all the gradients could lead directly to this green dot. And second, we have a non-linear but convex model, and there is only one global optimum here. The shape of it looks like a bow, and there is only one green dot, so it is very easy to using the current convex optimization methods to solve it. However, we can see that this is the real troublemaker, the nonlinear and non-convex problems. There could be multiple local optima for it, and it is very difficult to solve it. So, is there any problems? Is there any methods that can try to transfer the non-convex problem to a convex problem? And this technique is called convex relaxation. So our objective is to try to use this convex relaxation to solve more nonlinear problem in FGO. Now we will introduce a famous method in the convex relaxation named the Semidefinite Programming, SDP, and describe the bridge between the FGO and SDP. Now let's introduce some preliminary knowledge before the SDP about the polynomial optimization problem, POP. The POP can be traced back to the Hilbert's 17th problem in the century. He said that, can we rewrite a non-negative polynomial as sum of squares, the SOS? This problem is not well answered until recent decades. Some mathematicians like Lazarus find that for some problems, we can try to guarantee the optimality of a POP problem by testing the positivity of another function using the SOS. So what does he mean? Let us describe it yet step by step. First, we got a POP here, and then we can rewrite the original problem to a new function, the hx, using a given lower bound gamma. Then if we can describe the hx in a sum of square ways, we can prove that the hx is equal or larger than 0. And also we prove that the gamma is a true lower bound for our original problem. So if we can do this iteration more times, we can find approximately exact enough solution for our original POP. So in the following, we will try to use the SDP to solve this problem. And a question is that, what are the relationships between these problems? Now we'll describe them in this figure, including 3 problems: the FGO, the reformulated sum of square problems, and the SDP. And their cost function can be illustrated in the right figure. The blue one and the green one are the FGO and SOS. They share a similar structure here. And the yellow one, the SDP problem, provides the lower bound for these 2 questions before. And only the SDP problem is convex, since it has a unique global optima. In certain cases, we can find that, wow, luckily, we found their local optimum coincide. And what are these conditions? Now we provide 2 necessary conditions here, including the strong duality condition, the Karlsruhe-Tucker condition, and the tightly ranked relaxation condition, also named rank 1 condition. And in some cases, for example, in mild noise disturbance, they could also be sufficient. Now we can find that we can resolve the solution of the FGO by using the SDP under these 2 conditions. It's cool, right? So I will introduce 2 examples in satellite navigation to tell you how to employ this technique to solve more nonlinear problems. The first example is for the initial positioning using Doppler measurement. First, we got an FGO problem here, and it can be described here. It looks very complex. I will describe them step by step. First, we got unknown variables, including the 3D positioning of us on the Earth and the clock shift rate of the receiver. And the input includes the weighting, the Doppler measurement, the projected relative velocity. And why is this problem non-convex? I will explain it here. Both the constraint and the variable are convex, and the only reason for the non-convexity is that our cost function is the rational function. We also describe this in the right figure. As you can see in the right figure, the Doppler measurement is described by this conic surface with the vertex on the satellite. And our receiver should be located on the intersection of multiple conic surfaces, which could include multiple searching subspaces and local optima. So we have to solve this problem. We can try to use the SDP relaxation. To use that, we first reformulate this problem into a SOS form. And the only property of it is that all these functions are quadratic, except this one, the rank 1 condition, the rank 1 constraint. So we have to ignore it here. It is very troublemaker, and replace this equality with the inequality. Then finally, we can also find this after transformation, SOS become an SDP problem. So we have transformed the original non-convex problem with a rational function to a problem with convex functions. That's how we did it. So we applied this to a real experiment in Hong Kong. And we compare our methods, the SDP here, with the true local searching methods here, including the Gauss-Newton and the dogleg. You can find that when the initial point is near the ground truth, the Gauss-Newton and dogleg could be precise. However, if the initial point is far from our ground truth, for example, greater or equal than 1,000 kilometers, they could be trapped into local minima. Compared to that, our SDP method always provides certifiably global optimum without initial guess. It means that it can tell you that if it is successful or it failed, and ask for people for help. I mean before, yeah. So the SDP can also be employed for initialization for this local searching method to increase the accuracy. And finally, we can find that the localization accuracy of horizontal is only 122 meters. And the local searching methods could provide results in another country, maybe thousands of kilometers away. Now, we will give you the second example, the initial alignment also using the Doppler measurement. Here we adopt the model from an existing work, the GNSS, and the unknown variables here includes the rotation between the local world frame and the global Earth frame, and also the unknown receiver clock shift rate. Again, here the input parameters include the local receiver velocity, the satellite velocity, the line of sight vector, and the Doppler measurement. This problem is different from our first case. I will describe in the right figure and tell you why. As you can see, this process is actually the matching between the projection of the difference velocity with the Doppler measurement. And it seems that it is a linear model. So why is this problem still non-convex? The only reason here is that the visible region is belonging to SO3, the spectral orthogonal spaces, which is an internally hollow unique sphere belonging to the non-convexity space. So it could include multiple local optima in it. And our objective is to deal with this SO3. In this page, there are dense arrays of the formulas, so I will describe them step by step. I will transfer the FGO to SOS to SDP, including the variable, cost function, and constraint. First is the variable of our FGO problem. It is located on the SO3 and one-dimension real space. And this is non-convex. So we will first lift the non-convex variable to a convex linear space in the SOS. And the second, the cost function here is quadratic. It's very easy. It's convex. So we just simply divide it into a quadratic matrix. And then the constraint. This is linear. And the SO3 here, we can find that very annoying thing is that the determinant constraint here is cubic. It is not quadratic. So we find some existing work, they use the quadratic redundant constraint to replace it, and we use it. Finally, we get a beautiful SOS problem, and now we can use the Lagrange duality to get the SDP problem. Here, the variables are the Lagrange multipliers, and only one thing you should know is that this SDP problem is convex, since it only includes one global optima. Now our objective and key insight here is to solve the SDP problem and recover the FGO solution. Now we apply it to the real test in Germany. To simulate the GNSS degraded environments, we only use 4 satellites per second and motion in 60 seconds with at least 2 turning to protect the observability. This is a typical result from our test. We compare our SDP method with the GNSS, which use the Gauss-Newton, and it is a local searching method. We have only one data here, and we divide it into Berlin and Berlin 10. The Berlin here means that we use the data in its original frame rate. And the Berlin 10 means that we use it as a sparsified data and downsample it by the factor of 10. You can find that in the original frame rate, both the GVINs and SDP could reach the global optimum, and the yaw angle error is only 12 degrees. However, for the sparsified data, the GVINs can be tracked into local optima, since we use the random initialization for it. Compared to that, our ST method always provides global optima, and together with the certificate in both tests, and our error can be lowered down to 9 degrees. So, thanks for your attention. This is the summary of today's talk. First, we revisit the challenge from the non-Gaussian noises and nonlinearity in the state estimation. And second, we compare the state estimation methods, including the KFV, FGO, and SDP. Their relationship can be described in these two figures. And if you are interested in my work, you can also visit my GitHub website and find the open source codes and papers here. Again, I have to acknowledge my supervisors and collaborators, Lita, Weisong, and Matthew. Without their great help, I cannot finish these researches. So our future direction is based on our conclusion. We can find that both FGO and SDP cannot deal with the non-Gaussian and nonlinearity very greatly together. So our future estimator should be located at there. And we also know that the efficiency is also important in the real applications. And all the EKF and FGO and SDP are great in different types of levels. So our future estimator should be a practical method, just like the multi-state constraint Kalman filter, which is famous in SLAM. And our objective is to find a beautiful solution to combining all of this together to achieve efficiency, robustness, and certifiably. So I'm currently a PhD candidate in Hong Kong Polytechnic University and a visiting student in McMaster until this year. So if you are interested in my research on the certifiable navigation, please don't hesitate to contact me. Thank you.